Thank you, Lars. So, right, so I'm faced with the task of explaining ourselves and to the rest of you guys. So I will try to work on a very elementary level, or what I think is a very elementary level. So if it turns out to be more elementary, then I think please forgive me. I'm not trying to insult your intelligence. I'm trying to stimulate it. So our program is about the multiscale physics in plasma astrophysics, which means it's about how large and small scale fields interact. By fields, we mean electromagnetic fields and distribution functions. So if you like, in the more theoretical physicsy language, it's about mean field theory and fluctuations, and how the latter determine the former. So that's and vice versa, right? So that's the general setup. So I want to make something clear from the outset, which is that in astrophysics we usually deal with systems that are not in thermal equilibrium. So we cannot go ahead and write the distribution function just like that by maximizing something. The reason for that is because typically we're dealing with systems into which energy and often momentum are constantly injected, usually at large scales, but sometimes also at small. By large scales, I usually mean system size scales. By small scales, I mean much, much smaller scales than the large scales. Although I'll make it slightly more precise later on. And so as energy is injected, our systems, which are made of plasmas, usually are faced with an unceasing challenge of processing this energy and this momentum and facilitating the energy's thermalization. So what that typically involves is passing the energy from scale to scale, usually from large to small, sometimes in the reverse. The reason for that is because typically the scales of injection of energy, which are associated with macroscale dynamics, are physically distinct and therefore different, generally speaking, different in size from the scales of dissipation, which is to do with microscale plasma physics. So those of you who have previously heard of turbulence will be instantly alert at this point, because that's what turbulence is. I take a cup of tea, say, I stir it with a spoon. The macrophysics, the spoon is the macrophysics of the object, and the motions that I stir up must be dissipated by viscosity. I don't know how many of you have thought about how when you're stirring the tea, you're actually trying to heat it. Anyway, these motions must be dissipated by viscosity, and that's decided by the microphysics of the matter of which the object consists. So this happens at much smaller scales, and in between these scales, in between the scales of the scale of the spoon and the scale at which viscosity can deal with energy, there is a gap which must be bridged. So let's do some undergraduate physics. So I'm going to write the equation for the T, which is the Navier-Stokes equation. U is the velocity field of the fluid, and that I assume that most of you have seen this before. So this is the spoon. Okay. This is the viscosity, the viscous dissipation, and this here is the nonlinearity, which is responsible for passing energy from large to small. And so, the usual picture is that you make large motions. In subsonic fluids, these are we usually think of them as eddies because the motions are vertical. They break up into small ones, and those break up into even smaller ones, and eventually you get to small scales where viscosity can operate. Why are they small scales? Well, generally speaking, if viscosity is small, in order to make it match with all the rest of it, the energy sink that it provides to match with the energy input that the spoon provides, you need to make the Laplacian large. And so velocity field has developed large gradients, aka small scales, in order to do this. In between these scales, so at scales, say, that are much smaller than the stirring scale and much larger than the viscous scale, there is an interval of scales within which there is the dear to every theoretician's heart scale invariant regime where a power law for something can be derived.
Put a rho underneath your grad P.
Rho is equal to 1.
Oh, rho is equal to 1. You're doing water. Got it.
Well, rho is also 1 in T. Right. So in between these scales, as I said, there is you can derive a power law. There is a one-line derivation of what that power law is. If I have a typical energy at scale L, which I pass over to the next scale over characteristic time tau L, that's the energy flux through the system. And dimensionally, if I assume that everything happens locally in scales, this time is the size of the motion divided by its velocity, and out of this I get one of the most famous results of all time, which is the Kolmogorov law of turbulence. So this converted into a spectrum of energy translates into k to the minus 5/3, right? And that was done in 1941, and pretty much all of the turbulence theory that happened since has essentially been a footnote to this result. But this is only part of the story. It's only a part of the story because here I'm telling you about how a range of scales is excited, connecting injection with dissipation scales. Actually, in a large object, in a large inhomogeneous object, turbulence will change the mean properties of the system. So let me give you an astrophysical example, which is one of our favorite astrophysical examples of that. And that example is a galaxy cluster. So what's a galaxy cluster? It's great for theory because it's not very inhomogeneous. So it's a cloud of plasma sized about a megaparsec. The plasma is at about 10 to the 7 Kelvin. It's very diffuse, about 10 to minus 3 particles per cubic centimeter. This radiates an X-ray, so we see it right here. So we see it in X-ray. There is a whole industry of X-ray astronomy that looks at this. All of this is confined gravitationally in a dark matter blob, and typically at the center of this cluster there is a very messy black hole called an active-reactive nucleus that keeps spitting things out and stirring the medium. So turbulence arguably appears inside there. So a classic problem about this, a classic problem of, if you like, dynamics and thermodynamics of clusters is this. So we measure in X-ray what the temperature profile is of this thing as a function of radius. Let's make this radius. Okay. Typically, it looks about like that. All right, not particularly interesting in a way. This is about a factor of 3. And the problem is, why is it that there is no cooling catastrophe? What do we mean by cooling catastrophe? Well, this is a 10 to the 7 Kelvin gas that radiates. As it radiates, it cools. As it cools, it radiates even more efficiently, as it turns out. So the whole thing, if you look at the radiation properties of this thing, has to collapse down by about the 3 orders of magnitude to about 10,000 Kelvin, while also getting colder and clumpier and falling down towards the center of the cluster. So actually, what you're supposed to see is this, and you don't. So something must be heating this medium and transporting this heat around. Right? That's a simple problem. So let's do some undergraduate physics on that. So what is the equation for temperature in undergraduate physics? It's this, right? It's heat conduction plus source. And this is the heat diffusivity. This is the source. That's the AGN, actually, right? The heating engine in the middle. So you might think, okay, steady state. Solve this, and move on, thinking about cooler or perhaps hotter issues such as dark matter topological phases of matter, brief history of time, and stuff like that.
Is that in heat or is it cooling?
Sorry?
S. The sign of S. Is it heating or cooling?
Well, actually, it's shall I call it H minus C?
Okay.
Right. This is radiative cooling, and this is possible.
Which is bigger, H or C?
Well, they have to be balanced by that in this equation, right, to get a steady state. So, well, what is this diffusion coefficient? Well, this diffusion coefficient is, again, within undergraduate physics, that's a mean square step of a particle between collisions divided by time between collisions, which is the thermal speed of the particles times the mean free path. Right? That's well, actually, because this is a magnetized plasma, it turns out that you often have to replace this by the Larmor radius of a particle in a magnetic field divided by collision time, which is lambda mean free path over V thermal. So this is the microphysics of collisions. And it turns out that these kinds of estimates tend to prove very, very wrong. These numbers usually turn out to be either too large or too small. To give you a sense of the size of things, the mean free path in a cluster is about 10 kiloparsecs. So actually heat conduction is quite large, you might think, but because of the magnetic field, it's very small because the size of a Larmor radius revolving of a particle doing revolutions around the magnetic field is about 10,000 kilometers, which is, I think, by Californian standards, drivable. And so that's very small. So typically, you don't get anything good out of something like this. But let us look closer. The intercluster medium is in fact turbulent. I wouldn't have given this example had it not been turbulent. And so actually, what I have to do is this. There is turbulence. The temperature is advected by the motions of the plasma. So let me do a little calculation to show you how at this point we start getting very multi-scale here. So let me do this. Let me say that the temperature is going to be equal to some average profile T bar plus fluctuations. And I will... the nature of this average isn't very important, but you can imagine that you can imagine this as an average in time, or you can imagine this as an average because time domain observations of galaxy clusters are usually quite challenging. They're very long-term projects, which only organizations like this one can undertake. We mostly do to give you an idea, right? The evolution time of this is roughly the Hubble time, right? You can average over radial shells or something like this. So that's the average profile. That's delta T. I will assume that delta T is small compared to T bar, which indeed it is. Well, I can take this equation and average it, right? And what I will get is dt bar over dt plus divergence of average over of ut. I've taken u under the gradient because I'm assuming that my motions are divergence free, and on this side I have d delta t plus heating minus cooling. All right, so that's this story. Now this thing here is, so remember t is t bar plus delta t, and the average over the turbulence is 0, so this is actually u times delta t. So what we find is a kind of turbulent heat flux, which is a correlation function of two fluctuating quantities, the velocity and delta t. So it's the correlation functions of fluctuations on small scales that tend to determine the mean profiles on large scales. That's the basic idea of multiscale physics, right? So if we do a little further calculation to figure out what that thing is, well, I could say u of t, t of t. Let me try to calculate this average. I could do this. I could take this equation and integrate it formally in time. Okay, and say that this is an integral from 0 to t over t prime minus u of t prime dot grad t of t prime plus everything else. So average finished. And this here I will approximate, because fluctuations are small, as t bar over t. And what this will give me is an integral from 0 to t dt prime u of t prime dot grad t bar. And now this goes into there, and you see that what effectively has happened, there is a minus sign. And what effectively has happened is that right here I have a matrix which I can call turbulent diffusivity of this cluster. So in a sense, these small scale motions that are turbulent are changing the diffusivity of the problem, and so my original undergraduate problem can again become an undergraduate problem, but at the price of, in a manner of speaking, renormalizing the diffusion coefficient in front of there.
Remember the question?
Yeah.
From condensed matter people.
Yeah.
So is the sign of the thing defined? This correction, does it have to be positive or negative? Or?
Well, in simple settings, yes. Well, because it's u squared.
Okay.
Right? So
there's no
it's this thing here. Well, if this was in simple settings, right? So if this was an isotropic turbulence, and then this thing here would become basically just the integral over the correlation function of the turbulence times delta ij, right? And that would be simple diffusion. And of course, in realistic situations, when there are things are not isotropic, things are magnetized, there's all kinds of interesting life going on inside the cluster, all bets are off, and all sorts of interesting things can happen.
Does your Kolmogorov scaling break down at small distance?
At?
Small distance. Small scales.
Well, that's not particularly well known, just how far the Kolmogorov scaling in a galaxy cluster extends. We had a talk 2 weeks ago at a conference by an X-ray observer who was Irina Zhuravleva, who was showing us that if you measured, it turns out that you can measure these correlation functions in galaxy clusters, and if you looked at this spectrum, it extended much further down to small scales than you would naively expect based on some estimate of this sort. Okay, so but the nature of microscale dissipation and where exactly it happens and how far the Kolmogorov scaling goes and so on, these are all active research.
Energy injection at small scales.
You can have energy.
Telling us.
Yeah, I'll get to that. So now this diffusion coefficient, we can easily estimate it. So why is it different from what I did there before? Well, again, you can estimate it in pretty much the same way as I did before. So the molecular diffusion coefficient was V thermal times the mean free path. This diffusion coefficient is basically the size of the motion times the scale of the motion. Right? So physically what happens is that your particle, rather than going in random walk from collision with one particle to another, what it now does is it rides a turbulent eddy, traverses a certain distance, then the eddy disintegrates under it, and it hops onto another eddy and rides in a different direction, and so on. And that's again a random walk, but now the velocity of the motions involved is the turbulent velocity, and the size is the correlation scale of the velocity. Based on the Kolmogorov scaling, incidentally, this would be proportional to the 4/3 power of the scale, and so what you learn from that is that it's the motions at the largest turbulent scale that dominate such heat conduction if this scaling is correct. So now that's not the only thing we do. In a similar manner, one can think about momentum transport and turbulent viscosity. I've just told you about turbulent conductivity or turbulent diffusivity. Momentum transport, I already had an equation there, right? So that's my momentum equation. There's the transport of velocity by itself. And by exactly the same kind of calculation that I have shown you, I could manipulate this into a turbulent viscosity. If I assume that velocity, just like temperature before it, is decomposable in some large random flow plus some fluctuations. Large mean flow plus fluctuations. So a classic astrophysical example of the second situation is an accretion disk. So imagine a black hole. and there is matter spiraling around and into the black hole. That's what an accretion disk is. This system is Keplerian. All this matter has velocities, Keplerian velocities that go as 1 over square root of r, and it also has angular momentum that goes as square root of r, right? So if an accretion disk is an accretion disk, meaning that the matter spiraling around the black hole actually spirals into it, so it doesn't do this, it does eventually this, right? In order to do that, it has to get rid of this angular momentum because it's losing it as it's going down to smaller r. So as always as is always our luck, molecular viscosity of any plasmas that we're dealing with turns out to be insufficient to explain this loss of angular momentum. And so the question becomes, how does this happen? Right? So there must be, one concludes, turbulent transport. Right? In the same way that I could accelerate heat transport by turbulent diffusion, I could accelerate angular momentum transport by turbulent viscosity. Now, this situation immediately throws up a number of very typical astrophysical issues. So one is if there is turbulence, it must be dissipated into heat. The heat must be radiated away. Indeed, we see the disk, so something's radiating away. So from the luminosity of the object that we see, we can estimate how much turbulence there is. Because we're seeing the luminosity. The luminosity is the rate at which the turbulence is dissipating energy, so we could infer how much turbulence there is. So if we infer how much turbulence there is, we might infer how much transport that turbulence generates if we find a way to calculate its correlation, to calculate or theoretically or infer observationally these kinds of correlation functions. And so, if we know how fast angular momentum is removed, then we could infer how fast the matter accretes, and thus we can determine the fate of matter in the universe, as they say. The fate of matter in the universe is because, like the fate of everything, is to sink into a black hole without trace. A bit like the fate of grant money as well, things like that. So everything accretes in the world. In England, we don't have any grant money. And certainly won't quite soon have even. Anyway, right. So this is. I've said this, right, and everybody kind of either nodded or passively accepted that this was a good argument. But is it a good argument? Well, what's radiating from accretion disks is electrons. So ions are heavier, and they don't radiate as much or don't radiate at all. So actually, an accretion disk can fool us by putting all the turbulent energy into ions and then sticking the ions into the black hole, and we won't see any radiation. Right? So all these questions could have been viewed as fluid dynamics questions. This is now a plasma physics question. The plasma physics question is, how is turbulent energy partitioned between ions and electrons? Right? This is one of the classic disk questions. In an environment, I mean, again, you might ask, well, how does it matter? They collide between each other. Surely there will be equilibrium. No, they won't be. We are not in equilibrium, and typically the collision time between ions and electrons is very, very long. In disks, we are in a nearly collisionless environment, and so it is a meaningful question of how much energy goes into which species. So, well, you probably all remember, one of the big news of the year was the Event Horizon Telescope picture of a black hole, which of course was not a picture of the black hole. It was a picture of the accretion disk around it. Right. So.
Or jet.
Or jet. Well, there was no jet, was there? That's an interesting question, actually. Should one or shouldn't one see a jet? It turns out that the answer to the question of how electrons and ions are heated is crucial to deciding whether one will or won't. So this is a representation of a very, this is an instance of a very usual situation in astrophysics, because radiation in the end is what we observe. and it comes from particles that are heated or accelerated by some mechanisms, we are extraordinarily preoccupied usually with how particles are heated or accelerated, because that's our kind of observational handle on reality. It turns out actually that how that happens is too a problem in multiscale dynamics, but not in configuration space, but in phase space. I will get to that in a moment. But first, let me highlight another question that the accretion disk physics throws up, which is, where does this turbulence come from in the first place, right? So I said, assume turbulent transport. So there is a tragic fact about Keplerian flows in hydrodynamics, and that tragic fact is that they're extraordinarily stable. So it turns out that they're stable not only linearly, which is very easy to show, but even to large perturbations. So it's actually very difficult to create turbulence of a Keplerian flow, and for astrophysics it was a milestone when in the 90s it was realized that if it's actually a plasma that is magnetized, there is an instability now called the magneto-rotational instability that will produce turbulence. That, if you like, was a kind of a pivotal moment when astrophysicists, by and large, realized that they're dealing not just with hydrodynamics, but indeed with magneto-hydrodynamics. So Steve Balbus was to blame for this additional complication. So what is this additional complication? Let me show you what it mathematically looks like. Well, actually, I'll show you on that equation because I'll simply amend it. Right. So we had our fluid equation here. If there is a magnetic field, that means that there is an additional force. And that force looks like this. Current cross magnetic field over C. I'm writing this in the CGS system, even if it's against party line. Is it against party line?
No, CGS is great.
Good. Yeah, I mean, in England, that's pretty much the reason why we voted for Brexit, you see, to get rid of Système International. Silver lining to everything, isn't it? This here is a Lorentz force on particles. We use in our business in non-relativistic contexts, we use the pre-Maxwell version of Maxwell's equations. So the current is just curl B, and so it turns out that this whole situation with now the magnetic field can be written as a kind of additional stress. So let me rewrite this. Those of you who are extraordinarily fast with your vector algebra will see immediately that this is equal to BB over 4 pi minus B squared over 8 pi times unit dyadic, and the divergence of the whole thing. This thing here is called Maxwell stress, and just like viscous stress, and just like what's known as Reynolds stress, down there, it transports momentum, and it turns out dominantly as well in accretion disks. Now, the magnetic field itself is a dynamic object. So the magnetic field, well, this is again, if you like, undergraduate physics. Magnetic field obeys Faraday's law, and electric field in this Faraday's law is just minus flow cross B over C. That's the Lorentz force plus ohmic resistivity times J, and this converts this equation into something that looks like this. It turns out that this is yet again a possibility for multiscale interactions. So dB by dt plus u dot grad B equals to B dot grad u and plus eta Laplacian B. So each term in this equation is a field of astrophysics. This here is the transport of the field by the flow. So you can see, you can have anomalous resistivity or turbulent resistivity as well as turbulent viscosity and turbulent conductivity, right? That's what terms like this do. This thing here, if you think about this, stretches the field. So the flow can increase magnetic field. That's called turbulent dynamo. That's where we believe magnetic fields in the universe come from in the first place. You start with very small fields. This term will bring them up to the same energy density as the flow. And this here is ohmic resistivity, which is the only thing in this equation that can change the topology of the magnetic field lines. And that opens up a famous and fascinating field of so-called magnetic reconnection, of which I will say a few words further on. But I want to move on and tell you another. So these are all multi-scale problems in the sense that, I can ask how, for example, small scale turbulence will generate large-scale magnetic fields, or how large-scale magnetic fields will affect small-scale turbulence, and so on. So it turns out that magnetic field in a collisionless plasma is actually an even more pernicious object than it looks here. And the reason it's a more pernicious object is because particles follow it. If this is a magnetic field line, particles do, roughly speaking, this to lowest order, right? There is a Larmor radius, and it turns out that in all reasonable astrophysical environments, the particles' primary allegiance in moving around is to the magnetic fields, not to each other, in the sense that they execute many Larmor revolutions around the magnetic field before they collide even once between themselves. So it turns out that what that does, well, there are several things that this does. One of the things that it does is that it completely screws up the usual transport theory, right? So it turns out that what this means is that the particles will be transported as if they were unmagnetized along the field lines, but much more slowly across the field lines. So to lowest order in the Larmor radius, which, as I said, is usually very, very small in astrophysical environments, what will happen is your usual viscosity will stop being a nice Laplacian operator, but will start looking like this. Where little b is the direction, local direction of the magnetic field. You see, it's the transport that's restricted to gradients that are along magnetic fields. And similarly, your thermal conduction undergoes the same unpleasant modification, or rather pleasant modification, actually, because this is, of course, much more interesting. So now transport is primarily along the magnetic fields. And one thing that this means is that actually your magnetic field does not have to be dynamically strong in order to affect things dynamically. Because what happens is that everything depends on its direction, not on its strength, as long as the Larmor radius is much smaller than the mean free path. Okay, so the plasmas, you can have this regime in which the even weak magnetic fields can wreak havoc on your typical dynamics. There is another way in which they can wreak this havoc, an even more radical way, which is this. Let's think about a particle rotating around the magnetic field, and let's think about its angular momentum. That's mv perp rho, right? Where rho is the Larmor radius and v perp is the perpendicular velocity of the particle. Now, the Larmor radius itself depends on the perpendicular velocity of the particle. It's the perpendicular velocity divided by the cyclotron frequency, right? That's, again, undergraduate physics. And so this here is proportional to the perpendicular energy of the particle divided by the magnetic field, because the cyclotron frequency is this. It's EB over MC. Okay? So this quantity turns out to be an adiabatic invariant of particle motion as long as we're looking at scales that are time scales that are longer than the cyclotron period. Okay, so this is an adiabatic invariant, which means that all the cosmic dynamics which moves around the magnetic fields and flows and so on the face of it, has to satisfy the principle that every particle's mu, this is called mu, that every particle's mu has to be conserved. But what is mu? The sum of all mu's over all particles is actually perpendicular pressure divided by B, because pressure means mean energy density, right? So this means that even when I have very weak field, but enough to magnetize the particles, but it can be many, many orders of magnitude smaller than the dynamical strength. If I want to double this field, I have to double thermal pressure. So I have to double the thermal energy of the universe But even though typically in astrophysical environments, the ratio of pressure to magnetic energy is about 100. Right? So magnetic fields are 1% of the energy budget. You want to double them, you have to double the energy of the universe. Obviously, this is impossible, and nature has to find a way around it. The way nature finds a way around it is that it turns out that every motion that tries to change the strength of the magnetic field triggers very fast, cyclotron scale fast, and very furious microscale, Larmor scale instabilities that there's a whole zoo of them to be derived. They need the full machinery of plasma physics, kinetic physics, and their effect is to break mu conservation. Right? So you basically your large scale dynamics combined with the diabatic invariance means that without the help from microphysics you can't move. All right? So that's the story, and what that does is the effect of this is that we now have our plasma is now not just a macro scale object with mesoscale turbulence, which I previously referred to as the small scales participating. Now we also have micro scale, Larmor scale instabilities that are modifying transport and are producing some sort of anomalous collisionality in the process. So actually our systems are not 2-scale, they're 3-scale, right? We have the macroscopic scales, that's the object. We have the turbulence, and then we have microscales, which are Larmor scales. In fact, we have 2 microscales because we also have electron scales, and the ion Larmor radii, ions are heavier, electrons are lighter, so ions have much larger Larmor radii, and the ratio, just a second, and the ratio of these two things, rho I over rho E, is the square root of the mass ratio of the ions to electrons, which, for those of you who don't know, is approximately equal to 42, which is the answer to the ultimate question of life, universe, and everything. This was the question that they asked. Okay, so in plasma physics, everybody knows this, right? That's really where it is. So you had a question.
No, I think it's sort of about. Thanks.
All right. So these instabilities are an example of small-scale energy injection when we have large-scale flows or sources of free energy which can pump energy directly into the Larmor scales and create this seething mass of a seething sea of microscale instabilities. The challenge here is that it turns out that basically we have no workable understanding of the material properties of collisionless plasma, right? The challenge is to figure out what are the effective transport coefficients. So if you like, it's a kind of a 19th century style program, right? When people realize that things had viscosity and thermal diffusivity and so on, you have to conduct experiments, observations, numerical simulations, and so on, to measure them all up, and then the theoreticians have to come to the rescue and make sense of it all. Right. Let me finally go back to the question of particle heating. I said to you that we are very preoccupied with particle heating in astrophysics. Apart from the electron-ion energy partition, which I have already mentioned, there's another key problem in astrophysics, which is the acceleration and transport of cosmic rays. So these are high-energy particles that can be detected, that have a certain distribution that. For those of you who like distributions, they have an energy distribution which has a distinctive shape. There is a power law here. There is a little knee. There is a at something like 10 to the 16 eV, and then there is another power law, and none of this is properly explained. Right? So there's prima facie observational evidence that something interesting is going on, and so if we are to retain any self-respect as astrophysicists or as human species and so on, we have to explain it all. So the questions are this: how are such particles produced? Where are they produced? And how do they get from there to here? Right. So that's the typical. Now, how does one approach a problem like that? Well, first of all, we are now dealing with particles, not with a fluid. Right. So mathematically, that's described by distribution functions. So how do we write? And say f is the distribution function of these things. Well, it satisfies Liouville's equation, right? So that's what this looks like. Okay, and this here is V, and this here, well, the forces in our business are electromagnetic forces. So they are charge of the particle divided by its mass times electric field. And in principle, I could add to this also the magnetic field. So I can do the full Lorentz force, and this will make all hell break loose. And so for now, it's very interesting and actually the only relevant thing to do. But I will ignore this for now and just demonstrate to you how it works with in just this setting. So let me do. All the calculations I do in this talk are actually always the same calculation, right? I thought that was pedagogically well advised. So let me say that f. The distribution function, which is now a function of time, space, and velocity, right? So we have now gone into 6D phase space from what was previously a three-dimensional configuration space. So, and that is going to be some average distribution function. Let me say that it's simply just averaged over space. So it's going to depend only on V plus delta F. Right? So again, mean field and fluctuations, and yet again, I will assume that delta F is much smaller than F naught. Well, let's take this equation and integrate it over space. Okay? When I integrate it over space, this term will disappear, and what I will get is dF naught by dt equals to, out of this term, neglecting the magnetic field and keeping just the electric field, I will get minus Q over M d by dv dot E times delta F. Okay? So, and yet again, you see how this worked, right? So I put in F naught plus delta F here, right? The F naught, the electric fields are all fluctuating. So when I averaged over space, the E times dF naught by dv term disappeared, and the delta F is the only thing that remained. So again, I have a correlation function of fluctuations, E and delta F, which describes the flux of probability in velocity space. And I need to calculate this correlation function in order to, of the small scale stuff, in order to figure out what on large scales, both in energy in velocity space and in configuration space, what cosmic rays or any other particles do. Okay? So, right, well, let me do a little calculation of that. How do I want to do this? Well, I want to write first an equation for delta F, right? So let me now look what delta F does, right? So this is going to be d delta F by dt plus v dot grad delta F plus q over m e dot dF naught by dv plus q over m e dot d delta F by dv, and this is 0. Okay, so that's simply, I've simply subtracted that equation from this equation. Okay, and I will quickly neglect the nonlinearity here at my peril. Obviously, interesting things involve not neglecting it, but again, I'll do the simplest possible calculation. What I can now do is I can do the promised identical calculation to before, where if I want to calculate E times delta F, what do? I say E of t integral from 0 to t dt prime, and now I'm going to integrate this equation in time again. Okay, so this is going to be minus v dot grad delta F of t prime and minus q over m E of t prime dF naught by dv. All right. So now, I have two terms here, both of which again have meaning. First, let me look at this one here, right? So this term will produce what? It will produce minus q over m integral 0 to t dt prime E of t prime, like that, times dF naught by dv. If I ignore that term for a moment and just simply stick this into here, what I will get is a diffusion equation. Right? You see this. There is a minus q over m, and then I substitute this here. This times q squared over m squared is a diffusion coefficient. but it's now in a velocity space. So I now have, again, a thing like this. So what this says is that particles embedded in a sea of fluctuations, in this case electric fluctuations, will diffuse, right? This is called quasi-linear diffusion. What does it mean? They will diffuse. It means they will get heated, right? The distribution, you put in some distribution. If you put a Maxwellian into this into this equation and let it go, that Maxwellian will gradually become wider and wider and wider in velocity space, right? Because diffusion in velocity space is heating. Right? So now you might say, but what about this thing here that I've neglected? Well, that thing was neglected. So what did I really neglect? I said E of t times delta f t prime was negligible. Now, I can do this if the correlation time, so this is C at different times, so if the correlation time of my perturbations is short compared to any other relevant times here. And the relevant time here, you can read it off from here. It's k times v. It's the streaming time of the particles, right? So what this term here represents, which was this term, which was that term, is the fact that particles stream around and bring with them their probability distribution. Okay, so k is the typical size of fluctuations that they sample. V is their typical velocity. So if this is much smaller than 1 over the correlation time of the field, then the fact that particles sample the spatial structure of the fluctuations doesn't matter, and we get this diffusion effect, right? So each particle basically just sees an electric field doing this, and overall gets heated. Now, as you might imagine, all the interesting things happen precisely when you don't make that assumption. So it turns out that actually physically the effects associated with particles interacting with long-lived structures, with electric fluid and so on, are amongst the key topics of interest in today's astro. So let me very quickly give you an example of these topics, which will bring us straight to the kinds of questions that we have been litigating here in this program. Every morning we assemble and have a sort of a rambling discussion, which either reduces or increases our confusion on these topics. I think it's a diffusive process. So we gradually diffuse towards greater reaches of knowledge, but with a lot of steps back. One example is what happens in shocks. Right? So one of the things that might be sitting inside these correlation functions, right, is the fact that your particles traverse a cosmic environment which is full of shocks. Right? This can happen, for example, if we're thinking about particles living in supernova remnants, right, where there are shocks which they can interact with. Now, what's a shock? Well, it's a compressive front that propagates. Let's say it propagates this way, but Anatoly tells me that that's completely the wrong way to think about the shock, because the way to master the shock is to ride the shock. Right? I'm told that it's not a good idea to apply the same principle to mountain lines. But for shocks it works. Right? So here's a steady shock. We are moving with it, and there is stuff behind it and stuff in front of it. Stuff in front of it is stationary in the laboratory frame, and it's flowing onto the shock with a speed in the frame of the shock. Stuff behind it is actually the shock is faster than the flow that's behind it. So actually, in the frame of the shock, that flow is also flowing away from the shock. But because it's a compressive structure, this velocity is smaller than this velocity. So overall, there is compression. Now, this thing is filled with magnetic turbulence, the origin of which I will allude to in a moment. But let's say there is magnetic turbulence, and if you seed this with some particles, what the particles will do is they will be bouncing off these magnetic fluctuations and then diffusing out through the shock from the upstream region to the downstream region, and then bouncing again, turning around, crossing the shock, bouncing here again, turning around, crossing the shock. And what it looks like for a particle like this is what it looks like to a tennis ball or maybe a squash ball in a court with collapsing walls. right? So if you bounce a ball between the walls that are closing in on you, you will accelerate. Right, so that's called the first order Fermi acceleration, and that is how it is believed that particles get accelerated in shocks. So it's possible to show that this process has no preferred energy scale, and therefore you're going to end up with a power law. With a power law probability distribution of these particles. This is actually a very interesting multi-scale problem in itself. So remember, I've introduced it as a kind of the small scale to what was large scale of the universe, right? So the universe is large, it has this distribution of cosmic rays, but it's filled with small scale events like these shocks, where stuff happens, which go into that correlation function. But that itself is a multi-scale system, because the shock is a kind of a macroscopic fluid object, and then you have these particles. The reason there is turbulence is because, in fact, the presence of energetic particles triggers instabilities. So either associated with streaming of the particles over with the fact that they have a current across the shock. You can extract energy from a current. You can extract energy from streaming particles. So they create this turbulence. It sets up, as a result, some kind of then it saturates. Some sort of distribution of these particles sets up. They have a pressure. That pressure has a gradient. That sets the hydrodynamic environment for the shock itself. So the system is beautifully self-consistent, right? You have on the one hand all this microphysics of particles traversing the shock and getting accelerated. On the other hand, you're extracting their energy and turning it into fluid dynamics. So that's one example of this sort of thing that we're talking about. Another, and that's my last example, is something called a current sheet. So in magnetohydrodynamics, there is a tendency. Well, if you think about what a kind of a typical magnetic field configuration might be, well, there is a tendency for magnetic field to produce X points like this, right? So it's a typical arrangement of field lines. It turns out that such arrangements are unstable and that X points collapse into sheets. So these kinds of configurations turn into literally singularities so there is a magnetic field reversal along a very, very thin sheet, which in the absence of resistivity is actually a true singularity. And then what happens is that inside these sheets, this term gets activated, the resistivity of the matter. And so inside here, you have fields meeting like this, and the antiparallel fields reconnecting and turning into something like that. Okay, usually, so what is the reconnection? It's the breaking of the topology of the magnetic field lines, usually in energetically favorable direction. And in the process, you create a system where a current sheet where this reconnection is happening, and you find that matter flows into it through the long side and out of it through these nozzles. So you create a kind of a long-lived structure like that. It turns out that these sheets go unstable and actually break up into many magnetic islands, which then starts moving around, merging, eating each other, getting ejected, and so on. And so you create a kind of a one-dimensional turbulence inside this sheet. It turns out that if you seed particles into this energetic particles into this turbulence, what they will do is they will bounce about between those islands, and in a manner somewhat analogous to what I've said regarding the shocks, will get accelerated. So that's another fundamental way to accelerate particles. So these are the kinds of problems we're dealing with. The questions range from idle curiosity, such as, what are the correlation functions of turbulence in the galaxy cluster or something like this? What are the power laws, search for universality, these kinds of things, to what in astrophysics we refer to as, perhaps somewhat illogically, as practical questions, I mean, of course, all of astrophysics is entirely useless. But so practical questions are simply questions that are closer to observations. So we could ask questions as to, for example, can we predict the distribution of the cosmic rays that we see on Earth, or can we predict the temperature profiles that we see in galaxy clusters? Or again, sometimes that's another layer of usefulness in astrophysics. It's sometimes believed in astrophysics that the definition of something being useful is it having applications to cosmology.
Let's stop right there.
Which
Last questions.
yeah.
Sorry, maybe a bad point to stop you. Yeah, Ryan?
What was your last sentence going to be?
I was going to say that for example, one of the reasons we might want, if you are of the cosmological persuasion, right? So what you would do is you would say, well, if I want to know what the distribution of masses of galaxy clusters are, dark matter mass, right? What do you see? You see them in X-ray. You work out what the amount of dark matter there is based on the equilibrium of the matter inside that gravitational well. If there is turbulence, if there are interesting transport processes, and so on, that changes your calculation, right? So I don't particularly want to be stopped at that point, because that basically reduces plasma astrophysics to 10% corrections to the cosmological activities. I personally believe that the reason cosmology is useful is because it provides us with a reason to study galaxy clusters, which are fascinating plasma objects in their own right, and multiscale ones to boot. So that's what my sentence was going to be.
Oh, just a technical question. So over here with your tube of charged particles, is it useful, or would it be useful to, in fact, model that as a tube?
Well, every field line is a tube. Every field line is a tube, right? So field lines in vacuum don't really exist, right? But the field lines in the plasma are defined by the fact that if you make a little material tube around the field line, you can then follow the evolution of that tube through your fluid dynamics, and you can prove that but for resistivity, the magnetic field line will stay inside the tube. Then you could ask, what is the width of such a tube? And you asked a very good question, because the width of such a tube is actually precisely the Larmor radius of an electron. So if the field lines come together closer than that, you can no longer tell them apart, and they can reconnect. So actually there's another mechanism for a connection, which isn't ohmic resistivity, but a kind of a collisionless. It's a confusion of field lines, if you like, if you bring them close.
It's a tube with a charge density.
Well, the plasma is neutral on average, right? So there is on scales of order the Debye length, everything is quasi-neutral, right? So the tube it's a conducting fluid, but a neutral one.
So I have maybe a bit technical questions about this calculation. You repeated a few times. So it seems that basically the calculation tells us that the diffusion coefficient always renormalizes due to turbulence and gets bigger. So I don't know if it's true.
I don't think it tells us that it always gets bigger, but it does tell us that it always renormalizes in some way.
Well, I thought you said okay. Anyways, but
typically gets bigger.
Okay. So and it seems it also works for the viscosity itself. So my question is, if you're sitting at the transition, there is the Reynolds number, critical Reynolds number for turbulence or magnetic turbulence, and you basically perform this calculation, and it will tip you kind of above the critical Reynolds number. Is there some critical theory you can develop? Basically what I'm saying is that there should be some critical Reynolds number where turbulence just starts, right? So, and if you do this calculation right at the transition, can you develop some self-consistent theory?
Can it renormalize itself?
So remember, the renormalized viscosity or diffusivity associated with turbulence, renormalized viscosity, say, of turbulence, isn't actually a viscosity. It's simply it's a mathematical form that transfer of energy to smaller scales takes, right? So I drew a Kolmogorov spectrum earlier, right? This is the injection scale, this is the dissipation scale, right? I could draw a place, I could pick a scale, any scale, and simply say, if I'm confident that the energy travels this way in wave number, right, I could put a viscosity here, some effective viscosity that will remove the energy at the right rate. That's essentially what turbulent viscosity is. Right? So in some sense, on a very naive level, the turbulent viscosity, the turbulent Reynolds number of any turbulence is 1. That's it, what renormalizes to. Right? There are interesting exceptions to this situation because as I mentioned but didn't really explain, energy can sometimes travel backwards. Right? So when you're dealing with a turbulent system, especially a magnetized turbulent system, it's never quite guaranteed that you put in energy at a certain scale and it'll disappear to scales below and you will never hear from it. Right? There is such a thing as inverse cascades and so on.
It's two-dimensional.
Well, exactly. A good example of that in sort of atmospheric world is two-dimensional turbulence, right? Where it would be very dangerous to have models of turbulent viscosity, because then you wouldn't have. Well, actually, it wouldn't be dangerous, right? If we had turbulent viscosity in two-dimensional turbulence, then I suppose we would have less of a danger of hurricanes and all this. You know, Florida would be happy and etc.
Thank you.
Yeah.
Okay.